we have practiced solving a number of different types of inequalities, from compound inequalities to absolute value inequalities, or which are really just types of compound inequalities, and polynomial inequalities. The last type of inequality that I want to make sure that we have a pretty good grasp on before we move forward are rational inequalities. Now, an important thing for us to know is that when we are solving an inequality, we want to find the intervals that satisfy the inequality, that make that inequality true. Therefore, it stands to reason that we then need to first find the places or the values where that inequality can change sign from being positive or negative. Now, with rational inequalities, it's important to note that there are two distinct places where our inequality can change signs, or two types of critical values. There are the zeros, which we find by setting our rational, or our function, I should say, equal to 0. And these we can see graphically as our x-intercepts. And then there are also what we find the places where our function is undefined, or graphically we will see these would be our vertical asymptotes, or where our function's denominator is equal to 0. Now, I'm going to kind of outline a method for approaching rational inequalities and show you one other option, but stick around and listen to the full explanation so you can see where I'm coming from. So take, for example, this problem, where I ask you to solve and graph this inequality using interval notation. Notice I've got a variable in the denominator, so this is a rational inequality. The first thing I recommend doing when you're solving a rational inequality is to get 0 on the right-hand side and write this as a single fraction. So to get 0 on the right-hand side and write it as a single fraction. So let me go ahead and do that. So I'm going to go ahead and I'm going to take this inequality, I'll move back over here, take this inequality, and I'm going to say, all right, x plus 15 over x plus 3. And I'm going to move that 4 that's on the right-hand side over here and set this greater than or equal to 0. Now, in order for me to express this as a single fraction, I'm going to need to go ahead and combine these. And so I need to have the same denominator here for this term. So I'm going to multiply this by the same denominator over the same denominator. Now I can actually subtract these. So I got x plus 15. If I distribute this negative 4, I got negative 4x minus 12. And remember, all of this is over x plus 3. And this is greater than or equal to 0. And I can clean this up in a little bit. I can say, all right, x minus 4x, that's negative 3x plus 3 over x plus 3. So I've now successfully gotten 0 on the right-hand side and written this as a single fraction. Now, quick note. I know some of you are looking at this and you might be wondering, wait, couldn't I have just multiplied both sides by the denominator? In other words, written this instead as x plus 15 greater than or equal to 4 times x plus 3. And the short answer is yes, you can. But there is a danger in this approach. And compare what the original inequality was with what we've just written. And ask yourself, what might be the one danger here? And the answer is, by multiplying both sides by the denominator, or cross-multiplying here, you've completely now disregarded this denominator, which, if you recall, represents one set of the critical values we need to find where this inequality might be changing signs. So if you multiply both sides by the denominator, the danger is that you're now completely ignoring this denominator. Now, you can still do it this way. You can still go ahead and multiply both sides by the denominator, but you want to identify for yourself from the get-go that one of your critical values is the vertical asymptote x is equal to negative 3, because that is the x value that causes this denominator to be equal to 0. So if you're going to do it this way, really make sure that you remember that this is going to be equal to, that one of your critical values is equal to negative 3. Now, I always tell a lot of my students to kind of avoid that issue of doing it this way and then forgetting it completely. Go ahead and just make everything one fraction on the left-hand side. And this actually makes our life a little bit easier as we proceed with the other steps. So there's our first step. Go ahead, move everything over to one side and write it as a single fraction. Now, what's the second step? The second step now is to find the critical values, to find any critical values. And remember, there are now two types of critical values that we want to find. So as we see here, the first are the zeros, and the second are where the function is undefined. So let's go ahead and do that. So we're going to find the critical values here. The first one are the zeros. And we're going to find that by setting our numerator, and I'll just write NUM, our numerator equal to 0. So let's look at this. What was our numerator? Our numerator was negative 3x plus 3. We set it equal to 0. Negative 3x is equal to negative 3. X is equal to positive 1. This is our first critical value. I'm just going to label that critical value for short. So there's our first critical value. Okay. Next, what was the second critical value? It's where our function, all the x values where our function is undefined. So I'm going to go ahead and find that one. So we're going to say where our function is undefined, or what we call our vertical asymptotes. And to find these, we're going to set our denominator equal to 0. Set denominator equal to 0. And what was our denominator? It was back here. Our denominator was x plus 3. Okay, so let's go ahead and write that. So now we're going to set our denominator equal to 0. X plus 3 is equal to 0. X is equal to negative 3. Which again, if you did this by cross multiplying, you found that from the get-go. But now we see our critical values. Okay, so we have two critical values. Now that we found our critical values, we're now going to continue to solve this pretty similar to how we solved polynomial inequalities in our previous lesson. We're going to find the solution sets. And we can do this either by graphing or by testing our values. So take a moment right now and into your graphing calculator, go ahead and put this into your graphing calculator, or if you have Desmos right here, go ahead and pull up that graph. And what you should find, and let me see if I can pull this up. Just pull this over here. I'm just going to enter this in here as well. Just give this a second to load up. We've got negative 3x plus 3. And this is being divided by x plus 3. And let's collapse that so we can see this a little bit more easily. All right. And let's actually also graph that vertical asymptote, which we said was that x is equal to negative 3. And let's make that dotted to make sure that we know it's an asymptote and not part of the function. All right. So if we look at this carefully here, we're pretty much asking ourselves, when is this function greater than or equal to 0? When is this function greater than or equal to 0? Pause and see if you can write our solution in interval notation. Well, now that we have a pretty good sense of what the graph looks like, I'm going to go back to our notes sheet here. Okay. And I'm going to go ahead and sketch that graph. So what we saw from what we graphed was a vertical asymptote at negative 3, and at positive 1 was a 0. And this graph effectively looked something like this. And this is just a rough sketch. But what we see here is that our graph is greater than or equal to 0 here, which means for us our interval is as follows. We're going to say everything from negative 3, up until positive 1, all these are the x values that produce y values that are greater than or equal to 0. These x values here cause my function to be greater than or equal to 0. So our final solution set, we would say, is from negative 3 to positive 1 bracket. Now make sure we understand why we're putting a parentheses at negative 3. The original inequality was greater than or equal to. But remember, ask yourself, can we include negative 3 as part of our solution set? And the answer is no, because when we plug in negative 3, we see that our function is undefined. So where there's this vertical asymptote, we want to make sure we put parentheses around that, and we're able to indicate everything after negative 3 or greater than negative 3 satisfies this inequality. If you don't want to use a graphing approach to this, you can always just plug in values here. You can try plugging in a value that's less than negative 3, a value that's in between negative 3 and 1, a value that's greater than 1. But sometimes it's a little bit faster just to go ahead and plug our graph in. So kind of zoom out here so you can see the whole approach to this problem. Just to recap, again, what we did is we got 0 on the right side. We wrote it as a single fraction. We found our critical values, which are the zeros of the function and the vertical asymptotes. And then we graphed our function to find where our function was greater than or equal to 0, or where we satisfy that inequality. All right. I'm going to do one more example and then give you some time to try these on your own. If you flip on over to this back page, there's some practice problems for you to give a shot, and I've posted my solutions onto my website. But let's just go ahead and let's start with even something really basic like number 1. Pause the video right now and try this problem on your own, and we will work through it together. All right, so here's number 1. Let's give this one a go. So first things first, I'm going to move all my terms to my left-hand side. So 1 over x minus 3 is greater than or equal to 0. Now I want to write this as a single fraction. So I'm going to say 1 over x minus 3x over x is greater than or equal to 0. That then leaves me with 1 minus 3x over x is greater than or equal to 0. So there's step 1. Step 2, I'm going to do it in a different color. Now I'm going to find my critical values. So my zeros are where my function is equal to 0. So I'm going to set 1 minus 3x is equal to 0, negative 3x is equal to negative 1, and x is equal to 1/3. My other critical value are my vertical asymptotes, or where my function is undefined. So I set my denominator, which is x, equal to 0, and there's my second critical value. So on my number line now, let me do this in a different color here. On my number line, I can mark 0 and 1/3. These are the places where my inequality may potentially change signs. Take a moment and see if we can now graph this. And let me just pull up my graph here just so you can kind of see what this looks like. This graph here, if I just go ahead and put this in, I'm going to write this as 1 minus 3x, all of that over x. And our vertical asymptote we said was x is equal to 0. Okay, let me collapse that so we can see this. So here's what our graph looks like right now. And we can just tap that there. That's our 0 or our x-intercept. So what are we seeing here? We're seeing first off, there is a vertical asymptote at x is equal to 0. We know that. And we know that our graph is crossing the x-axis at positive 1/3. Everything beyond that is going to be, we see that everything on both sides of 1/3 after that, so everything greater than 1/3 is going to be negative. Everything beyond 0 going towards the negative infinity is going to be negative. So the only place where my function right now is greater than or equal to 0 is here. So how would I identify that solution on my number line? Again, I'm going to put a parentheses around 0. I'm going to shade in all my x values that satisfy the inequality up until positive 1/3. Right? Because all of these values from 0 and 1/3 cause my function to go above the x-axis, cause my function to produce positive y values. So I can move that out of the way. So we can see here, we see our solution set graphed, and then our final solution written as 0 to 1/3 inclusive. This is what I'm boxing as my final answer. This is the interval that satisfies the inequality. I see my solution set graphed on my number line here, and I use the graph to test my intervals. Again, if you wanted to, you could try plugging in a number here, a number here, a number here. But again, I think it's really beneficial to see the graph and see why exactly these values work.